Our problem statement is which design is best suited to counteract the possible scenarios that wind conditions or other environmental factors may cause the cable to vibrate and payload to spin out of control. With this in mind, we came up with a trade matrix to isolate each design and examine which one meets the criteria the best.
This is our trade study matrix. Each design criteria is weighted out of 100% in terms of priority. Safety is weighted the most because it is our first priority, since we want to minimize the human casualties and injuries in terms of both the rescuees and the users. Efficiency and ease of control are both weighted 20% because they both impact the safety. The more efficient and easy it is to control the hoist, the safer the hoist will perform overall. Cost and efficiency and the weight is both weighted 10% because we're a bit flexible since it depends on what exactly we want in the design. After grading each design's criteria, we calculate the weighted total to see which design is best fit for our final one.
Our rescue hoist will come with many official smart features. At first, we thought of using a weight sensor paired with LED lights. It will have notified us if the load was a safe weight or not by following a weight range for each LED light in the code. We are still considering this, but are hesitant because of potential wiring issue with the weight sensor in cable. We considered another solution where instead of using a weight probe, we decided on measuring the current needed to pick up the weight. We will have LED lights that notify the pilot of the payload. The larger the weight, the more torque it creates, and therefore the larger the current required. They're directly proportional. The LED light will turn on. When in range of 3 possible loads, the LEDs will be blue, yellow, and green. There will be a heat sink in the Arduino system cools down the hoist system. There will be a servo motor attached to a gear which will act as a stabilizer to counteract any outside forces, such as heavy winds that could cause the cable to spin. The servo motor will counteract the spin by rotating the cable in the opposite direction enough to keep the cable still. There will be also a camera. It will let the pilot see if there is something wrong with the cable and see general surrounding around it.
The final design is a combination of designs 1 and 3. We implemented several concepts from each design and chose what we felt was most convenient to use. We decided to incorporate a power switch, camera, current sensors, and LED lights because we felt that these components would make the hoist work in a safe and efficient manner. Initially, the design team wanted to use double cables, a scale, steel block, fan, and an additional camera. However, these materials were difficult to incorporate into the hoist system and increased the risk during rescue missions or putting us over budget.
The solution development tasks are broken into 5 artifacts, and this is how we approach them. For the digital collaboration, since no final code has been made, most solutions devised were put into a Google document since exact values could not be used. We created a GitHub account and a repo for the code so that when we began coding, edits can be made and versions can be pulled from the repo. The electrical schematic shows us where the power goes and what power is what. This will help us divide the code into smaller systems such as the servo motor, the stepper motor, or LED lights. Even though we are not making the full hoist yet, we can still test the critical subsystems we want. For example, we can test how to move the cable drum using a motor, as well as test one of our mechanical interfaces individually. They help us focus on the small portions so we can integrate it later all together. The flow chart is to help organize the coding and see what it's going to do. It tells which input leads to what and what decisions the code chooses based on conditions. It's a good tool that helps when making the final code because it's similar to instructions. Using a CAD or a mock-up/drawing, the mechanical development helps us visualize what we want our hoist to look like. If we see any issues later on, we can tweak the final design based on the visual CAD. This mock-up will help guide us in making the final physical hoist.